By the way, before we start our next sample problems, I'd like to discuss this. So this one is taken from the textbook by Philpott, and here in this figure, there's there's this illustration regarding the shape or the geometry of the shear and the moment. So it says here for okay, so we have here it says positive shear force diagrams. So if we have a shear that is constant, let's say we have a constant shear, then the moment will be linear, first order. Right? This one is zero order. So the moment will be first order. That's linear. But if our shear is linear, then our moment, change in the moment, would be second order. That's going to be quadratic. And the quadratic portion is that how do we know if it's this one or this one? Okay, so if we have this positive slope right here, if we have a positive slope, then this one will be, if you see or if you check the slope, actually it keeps on increasing. So the slope right here is actually increasing. Okay, so that's going to be the shape of the moment diagram. And if you have a linear, linear first order, but the slope is negative, then that's going to be the other way. That's going to be the other shape. So it becomes less positive. Okay, so when you say less positive, if you check the slope right here, uh, it becomes less positive, right? And right here at B, point B, figure B, if we have a constant, but it's a negative constant because it's below the zero line, then our moment diagram would be going downward. It's a linear, but it's going downward. It will have a negative slope. And if we have a linear shear, then and it says here it becomes more negative, right? So here is negative, but it's becoming more negative. So the shape of the moment or the shape of the change in the moment curve would be something like this, right? So again, you just have to visualize the slope at many points, and it becomes more negative. So something like this, because we have a negative slope. This one is negative slope, and this one would be positive slope. Okay, so if we have a linear, also negative, except that this one is positive slope, so meaning that it becomes less negative. So the shape of the moment curve would be something like this. Okay, now for our second sample problem. This one is again taken from the textbook by Philpott, and this is example 7.7. We have this beam right here, and it's loaded in distributed loadings of 1.5 kilonewtons, and the distance from point A to B is 4 meters, and from B to C this is 2 meters. Okay, so we are asked to determine the maximum bending moment that occurs in the span, and we can only determine the maximum moment once we have the shear and the loading diagrams. Okay, so first step is, for the solution, the first step as always is to solve for the reactions, support reactions. And if we apply the summation of forces y is equal to 0, and summation of moment, let's say at A is equal to 0, we'll get a value of this is AY is equal to 4 kilonewtons, and CY is equal to 2 kilonewtons. Okay, so let's draw it here. we have 4 right here. We have 4 kilonewtons, and right here we have 2 kilonewtons. Now let's draw the distributed loadings. We have 1.5 kilonewtons, and if it's a distributed loadings, then what we did here is to find the equivalent force or equivalent resultant force. Okay, we just have to multiply this 1.5k and to the 4 meters in order to get this value. And if you take this distance as well, then you can take the moments. So since this is just a rectangular, then the centroid right here, or the center point, would be 2 meters. Okay, so here's our loading diagram, and from the loading diagram, we said that we can draw the shear diagram. Okay, so let's start again at this point, and let's see what's happening in the. Let's base our construction or the shape of the shear diagram to the to what's happening here in the loading diagram. Okay, so at point A, it says here that there is a concentrated force of 4 kilonewtons, and there is also the start of the distributed loadings. However, at this point, this is 0. The distance here is 0, so therefore 1.5 times 0 would just be 0. So what matters is this concentrated force. So it says go up 4. Let's say this is it. So 4 kilonewtons. Okay, and since we have a distributed loadings, and what this says is that you have to go down. By the way, this must be 1.5 kilonewton per meter. This one per meter. So it says here you have to go down 1.5 kilonewton per meter. So that means that let's say we have a 1 meter. So okay, so let's say this is our 1 meter. So we have to go down 1.5, right? And another meter, we have to go down again 1.5, and right here, let's say 1.5 again, and right here 1.5 again. So actually the total is 1.5 times 4. Let's write here computations for shear. So from point A to point B, the shear value at B vis-a-vis B is just simply 4, right? 4 minus 1.5 times 4. So if you want this in equation form, this is also possible. And this will be 4 minus 6. This will be negative 2. Right, so right here at point B, we have a negative 2 value. Right, so this is going to be linear. Okay, so right here from point B to point C, since there are no loads from point B to point C, there's nothing going on, so that's going to be constant. And at point C, we have a concentrated load that says go up 2 kN. Right, so that's going to be, this is going to be our shear and moment diagram. Okay, and take note for this. Whenever the shear crosses the 0 line, because that's gonna be where the maximum moment will be at this point. Okay, so that's why we need to solve for this distance. And how do we solve for this distance? Okay, the distance that we know is from point A to point B, and that's 4 meters. So 4 meters. And let's say this is x, so therefore this distance right here, this will be 4 minus x. Okay, so since we have this value right here, and we have this value, then we can solve for the value of x using the similar triangle. Using the similar triangle, we can solve for x. Okay, so how do we do that? That's just simply 4. Let's just say 4 divided by the distance is equal to this -2 divided by the distance. Okay, so 4 divided by the distance, this is x, is equal to the value right here. This is -2 is equal to -2 divided by 4 minus x. And by the way, we shouldn't consider the sign, so let's just consider the magnitude. And if you shift solve this, what you get is x equal to 2.67 meters. Okay, so we need this x value, because if we are going to construct the shear and moment diagram, I mean the moment diagram, we need to solve for the area. And in order to solve for the area, we need also this dimension and this dimension. Okay, and therefore 4 minus x is just equal to 4 minus 2.67, and this is equal to 1.33 meters. Okay, so now let's label this area 1, this is area 2, and this is area 3. Okay, so computations, let's just write here computations for moments. Now for area 1, the area of the triangle is just simply 1/2 base times height. So if this is our base, this is our height, and it's just 1/2. So this is 1/2. Our base is x, this is 2.67 times height of 4, and this is equal to 5.34. Okay, and the unit right here is actually the unit of the moment, because this is meters and this is in kN, kilonewtons. Okay, so this will be kilonewton meters. Now for the area 2, this is 1/2 base times height still, except that it's gonna be negative, so minus actually the 4 minus x is just 1.33 times height of 2 divided by 2, so this is just minus 1.33. And what else? Now for area 3, this is the area of the rectangle, so we have a distance of 2 meters times, right, so this is the distance is 2 meters, and the magnitude of the shear is 2 meters, and this is just 4, actually -4. Okay, so now since we have this area, then we can actually construct the moment diagram. Okay, so let's draw another line right here. Okay, so from point A to, let's say this is point D, right? So let's say this is point D. Now from point A to point D, our shear diagram is in this configuration, and we have a negative slope, right? We have a negative slope, but we are in this positive region. So what that means is that and by the way, also, if this is linear, take note that the value of the geometry of the moment curve would be, if this is degree 1, then this will be degree 2 right here. Okay, and since this is positive, then the moment will also be positive, except that the shape is um, right. The shape, let's check if it's this way or this way. Okay, so since this is a negative slope, it means that if we are considering this curve right here, then this one is actually becoming more positive. Okay, becoming more positive. But this one right here, this is becoming more negative. Right, so the shape of this, because this is going to negative, so this must be something like this. And from point D to point B, so since this is negative slope, then the slope must be something like this, either going this way, I mean this way, or that way. Okay, so let's check. If we consider this curve right here, then that means that we are going less negative. But this one, the top curves right here, that's gonna be more negative. Okay, so that's gonna be our curve right here, and this is our maximum. And the value right here for the maximum is from 0 to 5 point to the area 1, because that's the change in shear. Then this is 5.34, and 5.34 minus 1.33, this will be actually this is just 4, because we have a decimal point right here. And from point B to point C, since this is constant, this is degree 0, then this will be linear right here, because it says -4, so we have a linear right here. So our moment diagram will look something like this. Alright, so that's all, and we'll do another sample problem for the shear moment diagram, and this will be our last sample problem. Okay, so here's our beam. We have these loading conditions. We have a 60 kN per meter, and that's going upward. And right here we have a concentrated moment of 140 kilonewton meter, and we have this concentrated force right here of 50 kN. And this is a cantilever beam. So that means we have this fixed end right here, and we have here a free end. Now, for the support reactions, you just have to You just have to apply the equilibrium equations, and what we get. And by the way, since this is a fixed support, then that's gonna be we are going to have a moment reaction right here, and we'll also, since this is going upward, then we'll also have a force that's going downward. Okay, and the value of this, and let's say this is MA, and this is AY. Now, by applying the equilibrium equations, the value of MA, that's the moment reactions. Okay, take note, this is moment reactions at A. This is equal to 120 kilonewton meter, and the value of AY is 130 kN. So let's write it here. This is 130 kN, and this one is 120 kN per kN meter. Okay, and we have to draw the external loadings as well. And this is 60 kilonewton per meter, and we have a concentrated moments here. This is 140 kN meter, and we have a concentrated load right here. This is 50 kn. Okay, now once you have this, then we can actually solve for the shear diagram. Okay, so let's start here. And right here we have a concentrated moment and a concentrated force, and also a distributed loadings. But this distributed loadings at zero distance is just zero. So what matters in the shear diagram is only is this AY, and it says go down 130. Okay, so let's go down 130 kn. Now from point A to point B. Okay, so from point A to point B. By the way, let's write here, or let's label here. This is V and this is M. Now from point A to point B, it says go up 60 kN per meter. So that's gonna be if we have a 60 times 3, that's gonna be 180. So let's solve it here. Computations for shear diagram. Okay, from point A to B. So our shear, the shear value right here at point B would be simply the the value of the load, which is 60. Right, 60 times 3 minus our value right here. This is minus 130. And this is just 100. Sorry, not 150, because 180 minus 130, this will be 50 kilonewtons. So that means that right here we have a 50 kilonewtons. Okay, so 50 kN. And this will be linear. Okay, so from point B to point C, we have actually there's nothing going on. There's no load, only concentrated moments. But take note, the concentrated moments only affects the moment diagram, not the shear diagram. Okay, so it will just be constant until it gets to D. Now at point D, it says go downward 50. Okay, so here's our shear and moment diagram. And right here we have this point where the shear crosses from negative to positive, and this distance right here can just be you can just solve this using similar triangles. This right here by similar triangles. Let's write this is x. X would just be 2.167 meters. 2.167. So 3 minus 2.167. This one right here would be 0.8833. Okay, so now for the moment diagram, again, let's start here at this point, at point A. Right here, we from the loading diagram, there is a concentrated moment, so there must be an effect right here. And whenever there's concentrated loads or concentrated moments, it produces jumps in the diagram. So since this is a concentrated moment, there will be a jump in the moment diagram. So right here it says we have a jump of 120 kN. I mean kilonewton meter, and this is counterclockwise, so that's gonna be negative. Okay, so let's write here from 0 to some value right here. Let's say this is 120. So 120 kilonewton meters. And we need another point right here to project. Let's just say this is point E. But first, I think we need to solve for the area computations for the moment diagram. So for the computations for the moment diagram, let's say this is area 1, this is area 2, and this is area 3. So area 1 is just, this is 1/2 base times height, and we have 1/2 times base of 2.167 times the height. This is 130, and we get a value of 140 point, let's say 855. Now for area 2, this is 1/2 base times height, and this is 0.833 divided by 2 times 50, and this is just 20.825. And for area 3, this is a rectangle. This is 2 meters, actually base times height, so the distance is 2 meters times the height. This value is 50 kn. 2 times 50, so this is just 100. Okay, so now let's solve for the change in the moment, and I just want to go back to our lecture handouts. Let's say for the rule number 4, we have here that the area under the shear diagram is equal to the change in the moment diagram, and our equation is just simply delta M is equal to M sub B, the moment at B minus moment at A. And right here, there's actually a typo. This is the loading, but it must be based on the shear. Okay, from this equation. Okay, so again, since we have the area, then we can have the value of this delta M, since this is the area under the shear. And if we have the initial value of moments, then we can solve for B. Okay, so this is going to be our working equation. Okay, so solving for delta M from point A to point E, moments from A to E. Okay, so our working equation is delta M is just simply M E minus M A, and we have this value, we have this delta M because of the area, and what we want is the value of ME. So ME is just equal to delta M plus MA. Now the delta M is the area, and this area is actually, this is a negative, I think this is a negative area. This must be, I think, a negative area. And the shear right here should be negative. Alright, negative, so that should be negative. Okay, our delta M is 140. So this is negative 140.885. Right, plus our value of M sub A. This is, okay, so since we have a concentrated load, this should be negative 120. So plus minus 120. Okay, and this will be negative. This will be 260. Negative 260.885. Okay, so that's from, let's draw it here. So negative 260, and this will be, the curve will be something like this. And once it crosses, right, this is negative, so that's why the slope here is negative. And since from point E to point B, that's a positive slope, so that's going to be something like this. It will just continue. But what is this value? So m from E to B. So MB is just simply equal to delta M plus M sub E. And what is this delta M? That's the area 2. So this is positive, so this will be 20.825. Okay, plus the value of moment at E, which is minus 260. So minus 260.885. So this will be minus, right, because it's negative, minus 240. So let's label it here. This one is negative 260.885, and right here is negative 240. Okay, so here it is. By the way, I think we should have separated this distance. So we have area 3 only at this portion, and we should have area 4. So area 3, this will just simply be 50, because 1 meter times 50, and area 4 is just simply 50. Okay, so the reason for that is just simply because there's a concentrated moment right here, and since this is a degree 0, then it will be from point from point B to point C. We will have a value right here. So if we do computations again, M from B to C, then MC would just simply be delta M plus M sub B, and delta M is 50, okay, plus minus 240. Okay, so that's going to be negative 190. So right here is going to be negative 190, and we have a concentrated moment of 140, so that's going to be 190, negative 190 plus 140. So there will be a jump right here, and another one would be somewhere right here. Okay, so just to have a brief review of what we did is that we have this given beam conditions, the loading conditions and support conditions, and we first draw the support, I mean the loading diagram by solving the support reactions, so we can draw the loading diagrams. And from these loading diagrams, we construct the shear diagram. We just apply the rules, and sometimes we need these computations just to follow through, or so that we can keep track of what we are doing. Okay, and whenever there's a cross from negative to positive or positive to negative in the shear diagram, that's where gonna be the maximum value of the moment. Okay, so that's why we need to compute this distance, and to compute this distance we use the similar triangles. And after that, once we have all this ready, then we solve for the area. We divide this into segments, and we cut this, I mean we cut this into segments and solve for the area. And we just have to take note that whenever there's a concentrated moments in the loading diagram, there will be an effect right here. Okay, so that's all for the shear moment diagrams, and in the next video we'll be discussing probably the moment of inertia or the stresses. All right, so see you in the next video.